Hi, my name is George, and our project is on a geometric approach to recycling cans using vision-based manipulation. The project demonstrated the full manipulation pipeline we learned throughout the semester, including segmentation, normal estimation, inverse kinematics, and etc. The problem that we're trying to solve is that cleaning the pollution and litter in oceans and parks require lots of human effort, and hopefully with automation we could reduce the risk on humans as well as improve the efficiency. In our simulation environment, we set up an IWA, a recycling bin, a surface with some cylindrical cans at random poses, and a camera at the top for perception. The manipulation pipeline is shown on the slide. The captured image from the camera is fed into the perception system with some pre-processing, and the grasp poses needed for each of the cans are calculated. Then, with a nominal trajectory, the inverse kinematics is solved and optimized in Tedrake using mathematical program, and out goes the joint commands to actuate the IWA.
We applied a lot of what we learned in class this semester to create a vision-based perception system that started with raw camera images and outputted poses to grasp the cans in the scene. However, since we had multiple cans in the scene, we had to be a bit innovative at some points in the pipeline and had to deviate from lecture, namely during segmentation to create masks for each object and the final grasp pose calculations. For segmentation, there's the problem where the camera doesn't inherently know that there are multiple objects, so we had to come up with a way to process the mask and output a separate mask for each object. This is commonly done with mask RCNN, but we specifically wanted to implement this project purely with geometric approaches and not use learning. Our solution was to find pixels in our original mask that correspond to an object and checked all neighboring pixels to find each contained blob. And we made an assumption at the beginning of our project that no two objects can be touching to make our lives a bit easier, so each of these blobs is a separate object. And now that we can distinguish the objects in the scene, we can just use what we learned in lecture on each object to produce a point cloud and estimate surface normals. And then this is where we deviate from class again. We had a piece set on antipodal normals as a heuristic for generating grasp candidates, but since in our project we were only using a camera from above, you can see in the vertical can case on the left, there likely isn't an antipodal pair of normals. So instead, our solution to determining grasp poses was to take advantage of the geometry of cylinders. First, for some pre-processing, we filtered the normals and only kept ones that were sufficiently vertical and off the ground. And because of the geometry of a cylinder, there are only two cases for how they can be positioned, vertically or horizontally. And in both cases, the average position of the vertical normals in the XY plane was approximately equal to the center of the can from above. And so this can be used as the position for a grasp pose. And then to determine rotation, for vertical cans, it can be any arbitrary rotation that matches the gripper frame where the y-axis is pointing down. But since the height of the can is longer than the width of the gripper, in the horizontal case, it's looking more like the door opening problem. So we just need to estimate the long axis of the can in order to determine a grasp rotation. And again, because of the geometry of the cylinder, the linear regression through the positions of the vertical normals in the XY plane of a horizontal can is approximately parallel to the long axis of the can. And now with all that, we're able to calculate pre-grasp and grasp poses to be fed to our motion planning system.
So this is the IWA in action. The nominal trajectory is defined by dividing up the motion into several time segments from pre-grasp pose to grasp pose to a few waypoints and back. Between any two poses, the IWA linearly interpolates the translation and rotation. It is similar to how the door opening problem in set 5 in that our algorithm also does optimization based inverse kinematics, converting the n effector trajectory into joint space trajectory using mathematical program to solve for the optimization. Further work of the project may include trying out sampling based motion planning algorithms like RRT, as well as having higher fidelity models of the bins and the cans, and maybe placing objects that are not cans in the environment to test for the robustness of our vision-based algorithm as well. And that concludes our presentation. Thank you.